Welcome back to the deep dive. So today our mission is to take this just absolute flood of new humanoid robot videos and really drill down into what's actually going on.
Yeah, there's been so much.
So much. And we want to go beyond, the slick music and the fancy camera work to find what you could call the hidden truths about stability, about dexterity, and I think most importantly, what the editing might be hiding. I mean, over the last few weeks, the internet has just been buzzing. You've got videos from 1X, from Tesla, from Figure, and they're all sparking this huge debate about what these bots can actually do versus what we're being shown.
Right, the gap between demo and reality.
Exactly, is today.
The goal being when you see that next viral clip, you'll know what to look for.
You'll know exactly where to look, not at the flash, but at the physics. Okay, let's unpack this. And I think we have to start with a video that has generated maybe the most controversy and awe lately.
It has to be the 1X Neo.
The 1X Neo bot, yeah.
Yeah.
The latest Neo Gamma version carrying what looks like a ridiculously heavy bag of rice.
That video was, it was a masterful piece of marketing, for sure, but it was also a really crucial demonstration of mechanical control.
Right.
On the surface, everyone just sees strength. But when you actually analyze the kinematics, the dynamics, the real achievement isn't brute force lifting. It's an incredible display of dynamic stability.
Okay, so stability, not strength.
Exactly. Stability under a changing asymmetric load. That's the real insight here.
Okay, so let's ground ourselves in the numbers then, because the scale of the challenge here is what really sets this video apart. Our sources are estimating that the load is a standard 50-pound bag of rice.
Basmati rice, yeah.
Which is already impressive, but here's the real aha moment. The 1X Neobot is like a lightweight in this field. It's only about 70 pounds.
And that weight ratio is everything. Just think about that. The robot is carrying something like 70% of its own body weight.
That's like a 150-pound person carrying a 105-pound person.
It's a huge deal. And when you look at the competitors, a lot of other humanoids are much heavier. They're often 150 pounds, sometimes more. They actually use that mass for stability.
For inertia.
For inertia, exactly. Neo can't do that. It's too light. Its stability has to come entirely from these lightning-fast active control systems, and that really is why the video is so compelling.
But, and this is where we start getting into those hidden truths.
Yeah.
The context of the task is just, it's immense. What's the one crucial action that's just completely missing from the video?
The initial lift. The acquisition. We absolutely do not see the bot lift that 50-pound bag off the floor.
Right.
We don't see it stoop down, we don't see it grasp the bag, and we certainly don't see it bring it up to its chest. The bag is transferred into the robot's arms by a human.
By Brent, the operator. And that transfer, that one little detail, is so important. Let's really expand on why lifting it from the floor is just a whole different universe of difficulty compared to just carrying it.
Well, when you lift something heavy from the floor, the robot has to go from a stable low crouch to a really unstable upright position. And during that whole move, the center of gravity, the cog of the entire system robot plus the load, it shifts dramatically.
So all the stress is on the legs and the core.
Maximum torque.
Okay.
The actuators in the legs and core are under maximum stress just to start the movement. They're fighting gravity, they're fighting leverage, and they have to accelerate this huge mass from a dead stop.
And from a mechanical engineering perspective.
From that perspective, if the bot is crouched, its motors have to generate just massive amounts of torque to push the knees and hips straight. That means a huge power draw, incredible forces across all the joints, and you need absolute precision to manage that cog as the load comes off the ground.
So by skipping that whole phase.
By skipping that, the demo becomes a test of, let's say, carrying endurance and stability management. It's not a test of peak lifting strength.
No.
Not at all.
Which brings us back to that anthropomorphic insight. We know as humans, if you lift with your back instead of your legs, you're in trouble.
Exactly. If it looks hard for a human to do with bad posture, you can bet the bot's actuators are probably screaming right at their physical limit.
Okay, so given that it's a stability test, let's break down the mechanics. Why does the 1X Neobot succeed so well in the carrying part? It seems to come down to what our sources call near-perfect posture.
It's all about posture and smart load distribution. The genius is in the passive support structure the robot creates.
Okay.
If you look at where that 50-pound load is actually resting, you see three really clever mechanical efficiencies. First, look at the hands.
They're completely open.
They're wide open. They are not gripping at all. That means zero power, zero strength is being asked of the hand actuators, which are usually the most complex and weakest part of the system.
Okay, that's one. What's the second?
Second, the bag is resting securely in the valley that's formed by the bent elbow. The forearm and the upper arm create a kind of rigid shelf.
So it's not holding it, it's cradling it.
It's cradling it. It's diverting all that force away from the delicate wrists and fingers and into the core.
It's basically turned his arms into a passive support beam.
Precisely. And that shelf structure funnels the force straight down through the torso and into the legs. That 50 pounds is split, roughly 25 pounds per side. And that force is managed by the big, robust joints in the shoulder, torso, and hips. And crucially, look at the knees.
They're straight, almost locked.
They're almost perfectly straight the whole time.
Why is that straight knee observation so important? Why should you, our listener, look for that in these videos?
Because if the knees were bent, even a little, the robot would need to constantly supply a huge amount of torque to those knee actuators just to stop itself from collapsing.
Right, just to hold the position.
But a straight leg, that locks the system into a structurally efficient column, like a bone. The motors are now just responsible for keeping it locked, which is way less stressful than actively holding a bend against 50 pounds. That straight posture is the biggest clue that they're prioritizing efficiency over just raw, continuous power.
And this all feeds directly into the physics of the center of gravity, the cog. I mean, you add 50 pounds to a 70-pound structure, the whole balance point of the system must shift wildly.
A shift in the cog is, it's the kiss of death for a bipedal robot. It's that simple. The cog has to stay centered over the feet.
Over that little contact patch.
Yeah. If the combined cog of the robot and the rice moves even slightly in front of the toes or back behind the heels, it just tips over. It's a non-negotiable physical law.
So what were engineers so impressed by?
They were impressed by the robot's ability to maintain a really strong static margin.
The static margin. It's like a buffer zone.
It's the buffer zone, yeah. It's how far the center of pressure, which is where all the ground forces are acting, is from the edge of the feet. A good static margin means you're stable. A narrow one means you're constantly about to fall over.
And to do this with a 50-pound bag of rice, which is not a solid object, the rice is moving around inside.
That's the part that's truly incredible. It's a dynamic, shifting load. So the robot isn't just reacting to its own movement, it's constantly reacting to the movement inside the bag.
How fast does that control system have to be to manage that?
Oh, we're talking about actuator response rates in the kilohertz range. Thousands of calculations a second. That low-level feedback loop has to be incredibly tight.
So a human can guide it, like walk forward.
Right. A human can say walk forward 5 feet. That's the high-level control. But no human brain can possibly manage the tiny micro-adjustments you need when the rice sloshes around during a turn.
We should also appreciate just the movement transition itself. The sources really detailed this. The bot wasn't just standing there. It moved, it turned, and it was on a carpet.
That's the real test, the carpet. Initially, yeah, the arms move up horizontally to get the load, and our sources think that was probably teleoperated, a human guiding the arms into place.
Makes sense.
But once it takes the load, the bot dips for a split second, absorbs the weight, and then immediately stands fully erect. It doesn't shuffle its feet, it doesn't lean back on its heels.
And the turn is where the real magic is.
The turn is where you see the autonomous success. When it rotates, it momentarily balances its entire weight, plus the 50 pounds completely on one foot while it lifts and repositions the other.
So it's hopping, basically.
Controlled hop, yeah. And that requires the dynamic control system to predict and execute a perfect weight shift to keep the cog over that single grounded foot.
Which is where we see that little stumble incorrect, that tiny wobble. For the listener, that isn't a failure. That's the whole point.
That's the entire movie right there. That stumble incorrect is proof positive that the autonomous neural net is fully engaged. It's the moment the system recognized, uh-oh, I'm about to lose stability, the static margin was compromised, and it initiated a lightning-fast correction to pull the cog back.
And if it were any slower,
even by a few milliseconds, the momentum of that rice bag would have just pushed it over the edge. It would be on the floor. That fast internal correction is the most telling sign of real progress.
So we've established it. The reason Neo's posture looks so good straight back, elbows creating that shelf, it's not a sign of pure strength. It's a sign of incredible engineering efficiency.
Exactly. They designed a way to manage the load that minimizes the strain on the motors, which lets their control systems focus all their processing power on one thing: dynamic balance. It's a very, very smart trade-off. They're proving the foundation is stable, and they're sidestepping the much harder challenge of high-torque lifting for now.
That discussion leads us perfectly into the next big thing, which is, okay, if the structural problem is solved through posture, what does that choice tell us about the hands?
Right.
So we're shifting from stability in the core to the difficulty of actually grasping and manipulating things. And this is where it gets really interesting. We have to keep saying it. That 50-pound bag of rice is a truly dynamic load.
It's not a dumbbell. It's not a rigid box. The rice flows. Every single movement, every turn, every step causes the rice inside to shift, constantly changing the pressure points on the robot.
Which is why those micro adjustments are so critical.
They're non-negotiable. If the high-level command is turn right and the bot starts to turn, the rice inside the bag will slosh to the other side for a split second, pulling the cog with it. The neural net has to instantly detect that shift and counteract it.
And a human can't do that with a joystick.
No way. It's impossible. Imagine trying to carry a full cup of water, but having to manually, with a controller, counteract every tiny ripple in real time. You couldn't. The fact that 1X did this is a massive win for their low-level autonomous control.
This dynamic challenge also really highlights the difference between the human and the bot approach. You see Brent, the operator, hand it over. He's using a tight grip. He's using his core and his legs. The bot, meanwhile...
The bot is using passive support and open hands.
Why is that bag itself so hostile to a robotic hand?
Well, beyond the shifting weight, the object's properties are just a nightmare for robotics. The bag is pliable, so it changes shape. It's made of slippery plastic. If you try to apply enough force to get a firm grip, which you'd need for 50 pounds...
You'd crush it or it would just slip out.
You'd either crush the rice or, more likely, the slippery plastic just squirts out from between the fingers before you can get enough grip force.
So the human solution is a conforming grip.
A firm, conforming grip that spreads the pressure. For a robot, that requires unbelievably complex hands with very precise force feedback sensors, which brings us right back to the design trade-offs between 1X and, say, Tesla.
Okay, let's zero in on the 1X Neobot's hand design, specifically that frozen CMC joint, the carpometacarpal joint of the thumb.
The CMC joint is what makes the human thumb so incredible. It gives us our range of motion, the ability to fully oppose the fingers. It lets us cup our hand, grip a ball, twist a key.
And 1X just fixed it in place.
They fixed it, which is a huge simplification from a manufacturing and complexity standpoint. Fewer joints means fewer motors, less weight, fewer things to break.
But the cost is dexterity.
A massive cost to dexterity. If the thumb is fixed, the robot can't do a true grasping motion. It can't scoop under that rice bag. It can't pick up a big, flat box. Its hands are essentially rigid paddles, which means they have to focus on strength and stability in the rest of the system because the hands are just not part of the heavy lifting equation.
So 1X chose robustness in the core over versatility in the hands. How does that compare to the Tesla Optimus hand?
Optimus is the complete opposite philosophy. It has fully opposable thumb. It keeps all those degrees of freedom in the CMC joint.
They're going for dexterity first.
Explicitly. That opposable thumb is the gateway to fine manipulation. It lets the robot handle a much wider array of objects, from tiny tools to delicate items. The challenge, of course, is that every joint you add compliance, you reduce the hand's payload capacity, and you make the control problem exponentially harder.
So Optimus is chasing finesse, while 1X is chasing what? Early utility.
Early utility and stability. It's the classic engineering problem, right? Do you build a strong, simple lever or a complex, precise instrument? And that choice tells you everything about their immediate goals.
Now let's bring in the physicist's perspective on this 1X demo to really nail down the limits. The idea of work done.
This is so important. In strict physics terms, work is force multiplied by distance. Since the robot received the bag at about the same height it carried it, and then just moved horizontally, the 1X bot did almost no work against gravity.
So all the hard work was done by the human.
All the potential energy, the work needed to fight gravity and lift the 50 pounds from the ground up to waist height, was supplied by Brent. The robot's job was just to maintain that energy state while moving sideways.
So it's not a lifting demo, it's a stability maintenance demo, a nuance that is completely lost on 99% of people who see the video.
Precisely. If they had tried to lift it from the floor, the power and torque required from the core motors would have been enormous. The energy use would have spiked. By skipping that, they proved their structure and control are sound, while staying away from the current limits of their actuator power.
And we notice a little subtlety in the video. Brent, the operator, seems really quick to take the bag back after the turn is done.
Yeah, that was interesting.
Is that a sign that this system was maybe running close to its limit?
I think that's very likely. While the bot handled the move, that dynamic sloshing of the rice would have put these sudden, high asymmetric loads on the shoulder and hip motors. That quick removal suggests the engineers knew they were right at the edge of the performance envelope for dynamic stability. They hit their goal-stable carriage, but they didn't push it into a long, high-stress hold, which again confirms the demo's focus on instantaneous control, not endurance.
That whole discussion about what is not shown in the video, the missing lift, it leads us right into this bigger essential topic for anyone watching robotics. And that's the whole issue of video editing and the search for real transparency.
This is the biggest hurdle for public trust right now, and it's universal. It's not just one company. These demo videos almost always use slick editing, jump cuts, clever camera angles to hide the failures, the difficulty, or the human help.
The moments of transition.
The moments of transition are always what's missing.
Let's get specific, using the sources we have, because once you know what to look for, you'll see it everywhere. What are the common missing moments?
Well, beyond the big lift from the floor, it's any task that requires high precision, low force control, or complex spatial reasoning. We almost never see the robot actually grasping the item.
Right, like the phone in the 1X video.
The phone is a perfect example. We see it kind of sliding, and then suddenly it's just secure in the robot's hand. We never see the fingers curl and scoop it off the flat table.
Which is actually really hard.
It's surprisingly hard. You need to get your fingers underneath a thin object on a flat surface.
And the other examples, the groceries, the vacuum cleaner, the wine bottle, they're all being carried, but we never see the pickup or the handoff.
The wine bottle is the ultimate case study in this. Okay, great. The bot is holding the bottle, stable carriage, check. But the real test isn't holding it. It's uncorking it.
Oh, yeah.
That requires one hand to stabilize the bottle, while the other hand applies huge multi-directional force. You need rotational torque and a linear pull-all without slipping or crushing the glass. If a robot is truly ready for your house, that's the moment we need to see.
And the fact that we don't see it tells us those mechanisms are probably not reliable enough to put on camera yet. The slick editing creates an assumption of capability.
It does. The viewer just assumes, well, if it can carry the bottle, it must have picked it up. But we can only confirm what we actually see.
And this even happens with teleoperated tasks, right?
Yeah.
Like the Tesla Optimus Diner video.
Absolutely. Tesla confirmed that was teleoperated. A human was guiding it. But even with a human brain in the loop, you could see the limitations.
It served popcorn, but it couldn't get the box itself.
Exactly. An operator had to carefully present the box to the robot. The bot wasn't asked to, say, take a single paper bag from a stack of bags, which requires vision and force control to peel off just the top one. Teleoperation solves the what to do problem, but it doesn't solve the how to physically do it problem.
So we have this industry trend of optimizing the videos, which naturally leads to skepticism.
Yeah.
But there's one company that seems to be trying to push back on that.
Figure, yeah. They've taken a very different path, really trying to prioritize transparency. They have a stated public practice of only showing autonomous actions in their main videos, and they insist on everything being in real time unless they say so.
And that wasn't just a random choice, was it? It came after they got some criticism.
That's right. Their first big kitchen video was criticized pretty heavily. People suspected a lot of editing, stitching together the best takes, maybe some hidden remote control, because the tasks just looked too smooth, too perfect.
So what was their response?
Their response was, frankly, revolutionary for the field. Instead of getting defensive, they released a raw, audited, hour-long video of their bot just sorting items in a warehouse.
An hour of raw footage. That's a goldmine. Why is that long-form, unedited video so much more valuable than a slick 90-second reel?
Because it shows the learning process. It validates it. The raw video intentionally showed the mistakes. You'd see the robot drop something, miss a grab, or slow way down to think. That gives you a true, raw picture of the system's actual performance. Engineers aren't just looking at success, they're looking at mean time between failures.
How long can it go without messing up?
And how fast does it recover when it does mess up? When you see a bot struggle for 20 seconds to grab something and then it figures it out and continues, that correction is the progress. A polished reel just shows you the one time it worked. The raw footage shows you the current state of the art, warts and all.
And that transparency, in a way, is a sign of confidence.
A huge sign of confidence in their underlying software.
So that's the ideal scenario we should be asking for. Give us the slick marketing video, sure, but then also release the raw 30-minute take so the engineering community can actually judge the real progress.
Exactly. The story needs to shift from look what we did once to look what we can do consistently.
Let's circle back one last time to how these trade-offs are physically built into the robots, and it all comes down to the hands. The humanoid hand is the ultimate engineering challenge because it has to balance two things that are almost mutually exclusive.
Strength and delicacy.
Powerful strength and just gossamer-light delicacy.
I mean, the human hand is arguably the most complex mechanical system there is. It needs the strong grip to lift a 50-pound bag, but then a second later, it needs the light touch to handle a raw egg or thread a needle.
This isn't a new problem. This duality has been the benchmark for robotics for decades. Our sources mentioned the historic egg challenge.
Oh yeah, the egg challenge. For years, that was a standard benchmark in university labs. The goal was to build a gripper that was versatile enough to pick up a heavy, solid metal weight and then immediately switch modes and pick up a raw chicken egg without cracking the shell.
Sounds simple, but it's not.
It's incredibly difficult because it requires two totally different mechanisms. For the weight, you need high torque and rigid joints. For the egg, you need exquisite tactile feedback, haptic sensing to detect pressure before you crush it. The challenge was getting one single hand that could do both reliably.
And that is the perfect lens to view 1X and Optimus through. Let's start with Optimus. When it picked up that paper popcorn bag, a lot of people criticized it for looking weak.
Right. But if you apply the light touch criteria from the egg challenge, you have to praise its ability to handle a deformable paper bag without crumpling it. A strong grip would have destroyed it. Optimus showed incredibly fine control over its grip force.
Which is tied directly to its physical design, the fully opposable thumb, all those degrees of freedom.
Exactly. Optimus seems to have decided to solve the complexity of the egg challenge first. They're prioritizing finesse and versatility.
They're making a bet.
It's a design philosophy that bets on control systems getting better and better. They're basically saying, we'll solve delicacy now, and brute strength can come later with better motors. And handling that paper bag suggests they're pretty far along that path.
And 1X, by contrast, prioritized the structural stability for that 50-pound load, which meant they had to simplify the hands. They had to freeze that CMC joint.
It was a pragmatic trade-off. They knew that showing high dynamic stability under heavy load was the most important thing for their first big demos. So they sacrificed the opposable thumb's complexity to create a simpler, more robust system where the load is borne by the torso and the legs.
So they solved the strength part of the duality by using the core, not the hands.
Their hands are for positioning and support, not for intricate manipulation. At least for now.
And we have to bring up that amazing little piece of trivia our sources found, which confirms that Tesla is 100% aware of this historic challenge.
Oh yeah, this is great. Tesla included a very deliberate Easter egg in one of their very first Optimus demo videos. There's a quick shot of the bot successfully handling a raw egg.
It wasn't just a random prop.
Not at all. That was Tesla speaking directly to the engineering community. It was a clear nod to the egg challenge benchmark, signaling that achieving that human-level dexterity, that balance of power and precision, is central to their entire design philosophy.
It's the ultimate test. Can you lift the 50-pound bag of rice? Can you pick up the raw egg? 1X showed they can carry the rice using their structure. Optimus showed they can handle the egg using their dexterity.
And that tells you where the industry is right now. It's specializing. There is no single robot that has convincingly mastered both ends of that spectrum at the same time, especially not autonomously and consistently. The next huge breakthrough won't be a robot walking. It'll be a robot lifting a 50-pound weight and then immediately threading a needle, all in one continuous take. That will signal the true convergence of strength and delicacy.
So what does this all mean?
So what this all means for you, the learner, when you see the next viral robot video is that you have to shift your focus completely. You have to look past the successful task in the highlight reel. Instead, you need to scrutinize the engineering reality.
Look for the hidden truths.
Exactly. Did the robot lift the item or was it handed to it? Look at the posture. Are the knees straight, which means efficient load management? Or are they bent, which means the motors are under huge strain?
And the hands.
And most importantly, the hands. Is it truly gripping, using an opposable thumb for active manipulation, or is it just using its forearm as a passive shelf? The real reliable progress is visible in that autonomous, low-level microbalancing that you can't even really see, and often it's visible in the mistakes that the best companies are now willing to show us.
That is a phenomenal summary. We've really unpacked these trade-offs. You have this incredible stability and load bearing from 1X Neobot, and that's contrasted with this clear, aggressive push for dexterity and fine motor control from Tesla Optimus. The engineers are just making fundamentally different choices based on what they want to achieve right now.
Yeah, different priorities.
Which leaves us with this final provocative thought for you to think about. We saw the 1X bot prove that a lightweight humanoid can carry 50 pounds of dynamic weight with near-perfect posture. That basically solves half of the strength problem. So now the question is convergence. Can we realistically expect a robot to achieve the classic egg challenge, that strong grip and light touch, while simultaneously being able to autonomously lift that same 50-pound rice bag from the floor in the next few years? What radical design trade-offs will engineers have to make to fuse that necessary power with that required precision? The next few iterations of these bots will really tell us if convergence is possible, or if specialization, the forklift robot versus the watchmaker robot, is the inevitable path forward for now.